All right, let's get started. Welcome back after 1 week of holidays. So today we're gonna revise binary search, and I have uploaded videos on binary search where we learned about how to search for target elements in a sorted list. It must be sorted in a way that we don't have to go through every element once. Okay, once it's sorted, we know the properties that the elements are arranged in a form from either lowest to highest or highest to lowest. And using this property, we can rule out some of the possibilities when we check whether a target element exists or not. Now, the way we check is follow the simple ideas that you check the middle element. So this is your range. So this is your search space. This is a sorted list. This is all you need to search. And your target element, say, is 33. Okay. And then instead of starting from the beginning, like we used to when we do exhaustive search, we start at the beginning, and then we go through each element one by one to check whether this is the target element that we want. But because this is a sorted list, it has a certain structure. Then instead of starting from the beginning, we take out the middle element, and then we make a comparison between these middle elements and the target elements. If the middle elements is equal to the target elements, then we already found it. So we only make one comparison. However, if it's not equal, there are only two other possibilities. Either it's lower than the target elements or higher than the target elements. If the middle element is lower than the target elements, that means if the target element exists, it must exist after this middle element. So we don't have to check the first half. We only need to check the second half. Now that's the beauty of it. Because it's sorted list, we know that every element in the first half that is before the middle element will not be our target element because the target element is more than the middle element. So we don't have to check whether each one of these is equal to target element anymore. Okay, so we only concentrate on the second half. So our search space is reduced by half. And then we apply the same strategy again. So this is our search space now, from 23 to 63 in this list here. We again apply the same binary search strategy. We take the middle element, which is 43, and then we make comparison between 43 and the target element 33. Now, the target element 33 is less than the middle element. So what does it mean is that if it exists, it must exist in the first half. It could not exist in the second half because every element in the second half is more than 43 because it's a sorted list. And we are looking for 33, which is less than 43. So we can rule out every single possibilities here without even checking because we already know there are more than the target elements, so it can't be there. So we only left with the first half. So we left with only 3 elements. So again, our search space is reduced by half again. Now we take the middle again. So the idea is we keep on recursively apply the same idea. This is called recursive, where we apply the same idea onto the list, where the list is shortened again and by half again and again at every iteration. So we again apply the same strategy. You take the middle element and you make comparison between the middle element and the target element. Now 33 is more than 29. So if it exists, it must exist after 29. So again, we rule out anything here. Anything here, which is only one element, we don't have to check 23. So we only left with 32. And at the last iteration, you only care about whether 32 is equals to 33. So at every single iteration, this is one iteration, one binary search, second iteration, second binary search, where you take out middle element and make comparison. Third iteration, you make another comparison, take the middle elements, make comparison. And then the fourth iterations, you make one comparison to check whether they are equal. If they are not equal, you know that it must not exist. The target element does not exist anymore. Okay, so this is the idea of binary search strategy. It doesn't check every single element because we can rule out some of these elements based on just a comparison with the middle element. All right, and eventually we only make 4 comparisons: 22, 43, 29, 32. Only 4. So it's an efficient way to look for an element in a sorted list. But remember, binary search strategy only works if the list is sorted. If the list is sorted, we can't say that we can rule out the first half or the second half when it's not sorted. Okay, when it's not sorted, we lost the property that we can rule out the first half of the second half because some of the numbers could actually still exist here if it's not sorted. Okay. Now, these are so far we're looking at binary search, like searching for a number. Now there are other applications of binary search that doesn't seem like you are searching, but ultimately you are actually searching. So let's look at one of these examples here. So this is a example where suppose I have a classroom of n students, n is some integers, okay? And suppose in Augusta University, all the classrooms are of the shape of square, okay? So it must be can accommodate m square seats for some m, okay? For example, a classroom of the shape of m equals to 1. So when m equals to 1, for example, then it can accommodate only 1 student. If I have a square of length 10, it can accommodate 100 students, okay? And if I have a size m, a square classroom of length, say 100, it can accommodate 10,000 students. So all the classrooms, suppose, is in this form, m squared, all right? The size, it can accommodate m squared seats for some value of m, all right? So the question is, if I give you this number n here, I have this number of n students, what's the minimum size of the classroom that I need? All right, so for example, okay, if I have n equals to 17, or start with n equals to 10, then what is the size of classroom that I need? It turns out I need a classroom of length 4, because length 4 will give me 4 squared, which is 16, is sufficient to accommodate 10 students. Okay, so I just request from the Augusta University, I need a classroom of length 4, all right, because it will accommodate 16 students, and 16 is enough for my 10 students here. Now, if I have 17 students, all right, then I will need a classroom of larger size, but I need to be optimized here, okay? What is the minimum size of classroom that I need for these 17 students? Now, 16 is not enough, right? So I need 5, a classroom of length 5. So length 5 square will be 5 square equals to 25. Now, 25 is enough to cover 17 students, okay? So for general n, what is the classroom? What's the minimum length of the classroom, or the square classroom that I need for these n students? For example, say n equals to 197. All right, so what is the length of the minimum length of the classroom, of the square classroom that I need to accommodate these 197 students? So once I know the number of students, say 197, all right, so I need to request for a classroom of certain size. I can only request for a minimum one, okay? So what is this minimum size? Now, what is your strategy here? So most of the students will immediately say, okay, let's take the square root, right? Take the square root of 197. See what is the number, all right? So let's take the square root. How do we form the square root? And you say, if I search online to find square root, I just use the library of math, okay, and do s square root of n. Okay, you say the square root of n is 14 point something, which means what? Which means I will require a classroom of size of length 15. Okay, so 14 point something. So again, it has to be an integer. So I'm going to round up to 15. So I will need a classroom of length 15. Okay, so a length 15. So a length 15 square. Okay, you give me this number of seats that can accommodate 197 students. Okay, now can we do it lower, say 14 square? So 14 square, a classroom of length 14 can accommodate 14 square students, which can accommodate 196 students only. It cannot accommodate 197 students. So one of the students will have no seat. So the minimum length of the classroom that I need will be 15, because 15 square will give me 225, enough to cover 197 students. It can't be 14, because 14 square is 196, which is less than 197, which means that 109, that means there will be one student who doesn't have a seat. Okay, so this is finding the minimum length of the classroom, square classroom that needed to cover this number of students for a given integer n. Now, suppose you don't have this math library. Suppose you are just given this number here, you have to do it on the spot. In the interview, they say that you have to find this number of students here. What would be your strategy? You don't have a calculator with you. What would be your strategy to find this minimum size of the classroom? So when you go for interview, for example, during the first stage will be phone interview. They ask you these questions and they don't allow you to use calculator. What would be your strategy? Now, you know what you need to do. You use the brute force search. There can only be some integer square that is greater than this n here. So you start with what are the possibilities of the length? Okay, so what are the possibilities of the length? So instead of saying that I need a calculator, let's start with what are the possible solutions? What are the possible solutions? Okay, what are the possible lengths such that the square of this length here is can accommodate 197 students. Okay, so you know that if I have 197 students, okay, what are the possible length of the square classroom? Okay, so if you have 197 students, okay, so the possible length of the square classroom will be from 1, it can be 2, and so on, all the way to n itself. Okay, you can have a classroom of length n, which is 197. It can accommodate n square students, but it's enough to cover 196. So these are all the possible length. Okay, it doesn't have to be that much. It can be lower than that. But given that you don't know how to do square root, if you have to do it manually, so these are your search space. It must be within 1 to n. And a classroom of length n can accommodate n square students. It's a lot more than what we need, but it's enough. Okay, we just need to find a search space where it's enough to cover these 197 students. And then we look for it one by one. Okay, so for each of these possibility, so we're gonna apply brute force search or exhaustive search. To find the smallest such length, okay, so we call it m, such that m to the power 2, okay, is greater equals to n. The smallest such m in these possibilities here, okay, or from m is from 1 to n, the smallest such m such that m squared is greater equals to n. Okay, we only look for the minimum length of the square classroom. Okay, and we're going to apply brute force search. And the idea of brute force search is always very simple. You try all possibilities. Okay, you start from your search space. The beginning of the search space, you test whether 1 square is greater equals to n. If it's not, you continue with the search whether 2 square is greater equals to n. If it's not, you continue with the next possibility, which is 3. Is 3 square greater equals to n, and so on and so forth. Your search space here is guarantee you to find one such element because I ensure that it's large enough so that it can cover this number of students. Okay, it can cover a lot more than that. I just be safe. I just make it so large. All right, so let's do our brute force search. We're gonna do iterations. So we're gonna iterate. M from 1 to n, inclusive. Okay, and at each iteration, so at each iteration, we're gonna test. We test if m squared is greater equals to n. Okay, if m squared is greater equals to n, because we start from the smallest one, which is 1, okay, then m squared is my answer. Then m is my answer, is the answer. Once you found something that is greater equals to n, you found it because we are looking for the smallest one and we start from the smaller one, from 1 towards the end. Okay, otherwise, we continue with the next iteration. Okay, so that's the idea. So we start from m in my search space is starting from 1, all right, all the way to n include n. Remember, range 1, n plus 1 will generate, so this range here will generate integers from 1 to n, not include n plus 1. This is a start value that we never include. So you include the start all the way, but not include the last element here, which is n plus 1. So eventually you stop exactly at n, okay? So for each of them, you're going to test if m squared, so this is the Python code for m squared. We already learned this many times. So if m squared is greater equals to n, if it is, we already found it. Remember, we are looking for the minimum length of the classroom that I need to accommodate n students. All right, so a classroom of size m will accommodate m squared students. And if this is more than n, then all my n students can sit in that classroom. Okay, and we're looking for the minimum one, which means once I found it, I can break. All right, so m is the answer, means we break. All right, so we're going to print, say, the minimum length of the classroom needed to accommodate these n students is m. Okay, and then we use the dot format to replace the curly brackets. Okay, which is n and m. All right. Good. And then we don't continue anymore. Once we found it, we break. So the idea of searching is always the same. Once we found it, we break. Okay. Now that means we stop iterations. Else we're gonna continue with the next one. Else, if it's not greater equals to n, that means it's smaller than n. That means a classroom of m, size m, length m, can accommodate m squared students, but this m squared seat is less than n. That means there will be some students who don't have seat. So we're gonna continue with the next value of m, with the next iterations. Okay, so let's try it. So it say that the minimum length of the classroom needed to accommodate this number of students will be 15, just like what we have seen before when I do the mat.square root. Okay, so in the phone exam, of course, you do it by hand. You start with 1 is not working, 2 is not working, 3, and so on. So you give an idea to the interviewer that you have a strategy, even though you don't have a math library with you, you have a strategy, what you need to do to come up with the answer. So the strategy here is to create this search space that you know definitely will give you where the answer is lying in this search space. And then you look for this one by one in a strategic manner. You start from the smallest one, okay? So that's the idea that you need to portray to your interviewer when you encounter these kind of questions, that you have a way to tell the computer how to search for these numbers, okay? Now, again, when we talk about programs, we start to think, or any strategy, is there a better way to do it, okay? So you have a possible length from 1 to n. So when you are given these questions without any computers or calculators, your first step is that I basically won't try 1. If my n is 197, I know that I won't try 1, I won't try 4, I won't try 2, and so on. And so I cannot have to reduce the space. I can somehow reduce the space, or I know that some of the numbers are too small to be able to accommodate this number of students. So then you think, besides exhaustive search, is there any other strategy that you have learned? So you have learned binary search. Can we use the idea of binary search in this manner, where we can reduce the number of check? Here we're checking basically elements starting from 1. All right, so binary search allows us to rule out some elements. All right, so in our case here, so let's just write here. So for n equals to 197, for this particular element here, we basically, we make 15 comparisons. All right, because we're gonna go through m from 1 to 15. Once it's reached 15, we get our answer, we break. We don't go to 16, we don't go to 17, all right? But before that, you do check 1, 2, 3, 4, 5, all the way. until 14, it still doesn't work, then you go to 15 and it works. So we make 15 comparisons. Now, can we shorten this number of comparisons? Can we not check so many comparisons? All right, so the idea again, we're going to use binary search. All right, so strategy 1 is to use linear search. Okay, so strategy 1 for linear search, we search one by one. All right, now strategy 2, we try to reduce this number of search, okay, using binary search. Okay. So again, when we talk about binary search, we need a search space as well. So again, this is my search space. Okay, I must ensure the search space can cover every, there must be, the answer must be in this search space. So to ensure that my answer in this search space, I make it large enough that it covers n students as well. Okay, again, this is very large. Okay, we possibly don't need that much actually. But the idea is we don't exclude this part, but we'll use our algorithm to rule out this. Okay, so we have our search space. So this is my search space. And this is a sorted search space. Okay, it has the property that we want, that if we can rule out certain elements. Okay, so what is our idea? So binary search is always the same. You take the middle element and you make comparisons. Okay, so we're gonna iterate. We are not iterating. So we take M, which is the middle of the search space, and then we make comparisons. Okay, if M square, now this time we are not checking a target element, but we can reformulate it into property that we want. Remember, the property that we want is that the minimum value of M such that is greater or equals to N. Okay, so let's try to do it. If M square, so if M square is equals to where M square sits enough to cover exactly all my students here. So M is the answer, we can break. Okay, once we found the answer, we break. We don't continue with any iterations. We don't make any more comparisons. Okay, now if it's not equals to N, there will be two possibilities. If M square is less than N, what does it mean? And the other possibility is if M square is more than N, then what does it mean? Okay, so again, binary search, we want to rule out the search space. We want to shorten the search space at every single iteration when we make comparison. So if it's equals to N, we found the answer. If it's less than N, all right, what does it mean? What is our search space going to be? If M squared is less than N, which means the correct answer could be more than, must be after this M, because it's not enough. M squared is not enough to accommodate these N students. So the answer has to be after this value. So my search space will be reduced. Will be increased to N plus 1. Okay, then I start with N plus 1 in my next iteration. Okay, so M squared is not enough to cover my students. So my next search will be a search for N plus 1. See whether N plus 1 can cover that number of students. Okay, now if M squared is more than N, all right, this could be my answer. Okay, so here our strategy is then my end will, I will stop. Okay, my end will stop at M minus 1 in my next iteration. So where's the start and end here? This is my start, my beginning of the search space. This is my end of the search space. Okay, so start is equals to 1 and end is equals to N. Okay, now I'm saying that if it's less than N, I can start with N plus 1 in my next iteration, because anything less than that is not important anymore. You know that there will be definitely less than N. Okay, if M squared is less than N, anything less than N will still be such that M squared is less than N. Okay, so it will still not be enough. So I should start with n plus 1 in my next iteration. If m squared is more than n, you know that, hey, it's already more than that. This could be the answer. So in my next iteration, I will stop at n minus 1 in my iterations. So that's the strategy that we're going to do. So we're going to do a very simple strategy, which is 1 to n. Okay, so as long as start is less than equals to n, we're going to do this test here. We're going to take the middle. So the middle will be start plus n divided by 2. Now here, my answer has to be an integer, so I do a floor division here. Okay, remember this is floor division, which means it's going to remove the decimal numbers. Okay, now and then I'm going to make comparisons whether my n squared is equals to n. If it is, that's the answer. We already found it. Okay, so I'm going to create a new variable for the answer. At the beginning is some value 0, for example. Okay, so answer will be equals to m, and then I break it. Okay, so I create a variable to store the answer. At the beginning, I set it to 0 or any other values. It doesn't matter. Okay, so answer is equals to m, and then I break. Now, if it's not, so there are two possibilities. If m squared is less than n, okay, then I'm going to start with m plus 1 in my next iterations. I don't have to worry about 1 to this number m here, because they will all be not able to accommodate my number of students here. So I will start my next check with n plus 1. Else, my end will be equals to n minus 1. Okay? Okay. So let's see. Here, okay, let's be very careful here. I have answer equals to m here. It only seems to break when answer equals to m. Okay? Or when start is more than end. Okay, so let's run this. Okay, so there's no, if you try to print answer, it says it's 0. What does it mean? It means that there is no value of m here, such as m squared is equals to n. Remember, my n here is 197. This is not a square number. There is no integer m such that m squared is equals to n. Doesn't mean that we don't have a solution here. It just means that the solution is in start and end. So let's check what is start and end. So let's print start. Let's print end. Okay, let's do it here. So very important, there are two ways to stop this iteration. Okay, there are two ways the iteration will stop. Okay, one is when m squared is equals to n. When m squared is equals to n, we hit the break. That means the iteration will stop. Okay, which is in here. Another way for the iteration stop is that when this is violated. Okay, when start is actually more than end, then the while loop condition is violated and it stops. It won't continue run. Remember, while loop means as long as start is less than equals to n. So when your start is more than n, you stop. It won't continue with the iterations. Another way to stop is that when m squared, you found a value m such that is equals to n, you also hit the break here. So there are two different ways to stop here. Okay, so if your answer is equals to 0, that doesn't mean that you didn't find the answer. You just need to look at what is this start and end. Why did it end? Why did it stop? So if you look at your start and end, we have this here. Okay, so basically what we have here is that start is the value, the minimum value for which m squared is actually more than n, and n is the value where is the maximum value m such that m squared is less than n. Okay, so this is where we stop. Okay, so start and end. If the iteration stops because start is greater than end, okay, that means what? That means start is the minimum value of m such that m squared is greater than n. Okay, and end, actually, these are variables here. And n is the maximum value of m such that m squared is less than n. Okay, so if the iteration stop because start is greater than n, it's not because you hit the brake. Okay, then start is the minimum value of m such that m squared is greater than n, because the way you move start is that if m squared is not enough to accommodate, I'm going to move the start to the next value. So m is the minimum value that would such that m squared is greater than n. All right, and n is the maximum value for which it is less than n, because else only happens, so this happens when m squared is greater than n. So when m squared is greater than n, and you're going to end with n minus 1, so you're going to move one step down. Okay, we're going to move one step down, which means n is the maximum value of the value m such that m squared is now less than n. All right, so if it is less than n, we're going to move it up. So it will be greater than n, hopefully at the end. And if it is greater than n, we're going to move it down, and we're going to reduce the search space n to down so that it is less than n. So we have now at the end, at the very end, the value of variable n here will be the maximum such m such that m squared is less than n. So this is exactly what we are looking for. We're looking for the value of m such that m squared is greater than n or equals to n, okay? And any other value that is less than this value m here must be such as m squared is less than n. So which means, okay, start is our answer. In this case, okay? So what we have here is that we're gonna copy here. We have answer equals to 0. So if answer equals to 0, that means we didn't find a classroom that is exactly can accommodate exactly my students, but we found one that can accommodate my students with some extra seat. Then my answer should be equals to start. Okay, and then you can borrow the print functions earlier on. Okay, just to print the answer. All right. So print is answer. Okay, in the end, we get the same answer. The minimum length of the classroom needed to accommodate this number of students is 50. All right, so we come up with the same answer between binary search. So this is my binary search implementation. This is my linear search implementation. Both give me the same answer. Now, they are both correct, but the question is, which one is more efficient? How many comparisons that we make? So let's see how many comparisons that we make here. Okay, so for your quiz, we're going to ask you to do this. So I'm going to do it one time here. Okay, so this is a slightly different version from what you have seen. If you should already watch the video on how to complete this table. So for the quiz, you will be asked to complete this table here. So today we're going to complete the slightly different table here, where we are finding, this is my answer here. Okay, so we have here n equals to 197. All right, and our property is m squared and so on. And we're going to copy this into my code here. All right, and let's see. So for starting from the first iteration, my start is 1, my end is end. Okay, this is my start and end. Is start less than equals to n? This is true. Start is less than equals to n. And what is the middle element? So it will be 198, 1 plus 197 divided by 2. Okay, 197 divided by 2. Again, you remove the decimal. Okay, so what is this number here? It will be 198 divided by 2, which is 99. Okay, so your middle value will be 99. Actually, I don't need this part here, so your middle value will be 99. Okay, now, if it's 99, I'm going to check. So m is 99. So m is 99. And I'm going to check if m squared is equals to m. So what is my m squared? Is it equals to n? Now 99 squared is definitely not equals to n. So this is false. Okay, if this is false, I'm going to check whether it is less than n or greater than n. Okay, so this is false. M squared is not. I'm going to create one more and check whether m squared is less than n. Now m squared, 99 squared is not less than n. All right, so this is false as well. So what will happen is that now your value of start and end will change. So this happens when m squared is actually more than n, so your n will move to n minus 1. Okay, so in your next iteration, start will remain the same, but your end will be this value minus 1. So it will be 98. Okay, and then again, is it true? The answer is true. Okay, and then you take the middle value, and then you check again. So what is the middle value? It will be 99 divided by 2. Okay, that will be 49. 49. If you remove the decimals, so this will be my middle value, m. And then I check whether m squared is equals to n. Again, this is false. Is it less than n? This is false. Okay, so 49 squared is definitely not less than n. So again, if it's not less than n, I move the n to n minus 1. So my n value here will be this value minus 1. It will be 48. And this is starting the same thing. And then I continue with that. It's true. We continue when it's true. And what is the m value? It will be 49 divided by 2. Okay, and that will be 24. And is 24 squared equals to n is false? Is it less than n is false? Then I keep moving down. Okay, so again, I follow this. It can't be. This when it's more, m squared is more than n, I'm going to reduce n to n minus 1. So my m here now is 23. I start with 1 and so on. Again, if it's true, I'm going to take the middle value to 12. And again, 12 squared is not equals to n. It's false. And 12 squared is 124. Sorry, 12 squared is 144. And this is more than my n. So this, is less than n. N squared. So n squared, 12 squared is 144 is less than n, which is 197. So it's true. Okay, once this is true, okay, once this is true, we're going to be here. M squared is less than n. Okay, so if this is true, we are in the else if statement, which means my start in my next iteration should be n plus 1. So my next iteration, all right, my start value will be this value, 12 plus 1, which is 13. And the n stay the same. Is it still true? They are start less than equals to n. This is true. And what is the middle value? So the middle value will be 36 divided by 2. And this will be 13. Sorry. It will be what? 18. Okay. It will be 18. Now, if m squared is equals to n, is false. All right. Is m squared less than n? This is false. Okay. So now, if this is false, we are looking at here, n minus 1 here. So in my next iterations, I start with the same, but my n will move to n minus 1. So I take this 18 minus 1, it becomes 17. And then, is it still less? It's true. And you take the middle value again. Now, if you continue this way, the number of iterations that you need to check, if you continue with this, is definitely less than 15. All right, because the next value, say, is 30, is 15. Okay, is m squared equals to n, is false. Is m squared less than n, is false. All right, then you go to the next iteration. Because this is false, start remain the same, and will be this number minus 1, which is 14. Now, this is false. 13 is not, sorry, this is true. This is still true, okay? And you take the middle value, 27. So 27 divided by 2, which is equals to 13. Okay, and is 13 squared equals to n is 4. Is it less than n is true. And then if it's true, now start is the one that's changed and remain the same. So start will be n plus 1, that will be 14. And this will remain the same. It start less than or equals to true. This is true again. And you take the middle value, which is 4, 4th, and this is true. And this is true. You go to the next iterations, and this will become 15 and 14. And this time it will be false. Okay, so in the end, how many comparisons that you need? 9 comparisons. So we have make 9 comparisons. So comparisons. So for binary, for n equals to 197, okay, we make 9 comparisons. Okay, opposed to linear search strategy. So linear search, we make comparisons of 15. So linear search, we make 15 comparisons, and binary search, we make it to 9 comparisons. This is for a particular value. So if you choose a higher value of n, okay, the distinction will be larger. Okay, so binary search for this particular value of n is definitely more efficient than comparing to linear search. And of course, you should play around with these numbers here. With the different numbers, you can see the distinction to be higher. Now that's all for binary search for today. We're going to do the quiz now. Thank you.